Hey, what's up, guys? Chung here again. And today, let's take a look at another LeetCode problem here. Number 494. Target sum. Another medium problem. Okay, so let's see what's the problem is asking us to do here. You're given like a list of non-negative integers, right? Right, it's either zero or positive integers, and the target s. Now you have two symbols, plus or minus. And for each symbols, you can choose from you can either do a plus or do a minus. And if and you need to find out how many ways to assign basically how many combinations, right? You can make, and so that the final sum is the s. In this case, it's 1 1 1 1, right? There are like 5 ways that it can make to the final 3 here. Okay, and yeah, so basically this is like a very like typical DP problems, and I'm gonna talk about two ways you can solve this problem with DP. And the first one is the traditional like recursive with like memorizations, which basically we start from the first one, and every time basically we have two options, right? We can either do a plus the current number or do a minus or subtract the current numbers, and we keep tracking of the current positions and also the current sum. And by the time we reach the last one, we check if the current sum is equal to s. If it is, then we return s, right? Otherwise, we just return 0. hmm So yeah, and that's the first one. And the second one is a more elegant. It's a very brilliant way of thinking this problem. It's like we can convert this problem into a 0 1 knapsack problem. Okay, so let's try to solve. Okay, let's solve this problem in the traditional way first. Okay, so in that case, we're gonna have a DP here. DP I and current sum. Okay, okay, I'm gonna write some um, of the DP here, the variables here, like the numbers, right? And then of course, we need the memorizations, right? That's the standard template for all the top-down DP problem, right? And then, actually we can, uh, anyway, I'll try to finish, write the first one here, the return DP. Yeah, basically we just return DP 0 dot 0, right? At the beginning, the current sum is 0. And then here we just do first we check, right? If the I and current sum is in the memorization. If it is, we simply return the memorization, right? Very standard top-down template. Okay, and then like I said, so by the time when the I reaches the end, reach the last, reach the last place, right? Which is the end in this case, because we are going to add 1. Then we check if the current sum is equal to s. If it is, we simply return 1. Else return 0, right? So this is like easy to understand. And then we're gonna have an answer, right? So the answer here, we just have two options basically. Every time we do I plus 1, and then the first one is gonna be we're gonna sum plus the current number plus nums I, right? And then the second option is the still I plus 1, and then current sum we subtract current number, right? And then other than that, just some once we have the answer, we just assign this one to the I dot sign. We just memorize the current answer, right, for the state, and we simply return the answer. Okay, so Yeah, so I think this should just work. Let's run the code here. Yeah, okay, so the test case passed. Let's try to submit it. Yeah, see, okay, so this one works pretty straightforward, like top-down DP, right? Basically, we just start from 0, 0, which is the first one, and at each step we have two options. We either like plus the card number, or we uh, subtract the current numbers, and every time we will remember the current state. Okay, a current state plus the current I here, because that's the basically that's the 2D state we're gonna use to remember our current state, because with the current with the I and the current sum, if this state has been that basically these two variables can uniquely identify the current state. And if this one has been calculated before, we simply return it. Otherwise, we just do the calculation, right? Straightforward and easy, right? Okay, so that's that. And is there a better way we can do DP here? The answer is yes. And let's think about this example here. Let's say we have the numbers we have is 1, 2, 3, 4, and 5, and that's the answer. That's the numbers we have, and the s is equal to 3. Okay, and then so one of the examples is going to be 1 minus 2 plus 3 minus 4 and plus 5 is equal to 3. Okay, right. So that's one of the basically that's one of the ways. One of the ways you can come up with the three answer here, three target, target 3. And the tricky part here is that if you move, right, if you move all the negative numbers to the right side of this equation, so what do we have? We'll have 1 plus 3 plus 5 equals to what? Equals to 3 plus 2 plus 4, right? And basically, so what's the total? So as you can see here, so here the total sum between for the left side and right side is what? Is the sum of the numbers plus s, right? So that's the left side plus the right side, because now we're converting all the numbers to the positive numbers, right? So that the total sum in this equation will be the sum of number that's 1, 1, 2, 3, 4, 5, and plus s. And then if we do a divide by 2, since they're equal, then if we divide it by 2, that's the numbers on the left side. Okay. Basically, that's gonna be our target on the left side, right? So now the question will become, as you can see, now the capacity, right? So now it's a backpack problem, because the capacity, or is this, right? The target, that's the capacity. That's the capacity. And the items are all the numbers. And basically now we just need to find out how many ways we can get to the exact capacity, right? Get to this exact capacity by either choosing one item or not, because in this case, as you can see, you can only use the number only once, right? So now the capacity will become the sum of this divided by 2, and the sex, or the items, so it's all the items, and the problem converts to how many ways we can use those items, and the one item can only be used at most once, right? So that we can get this capacity. That's a very typical DP, sorry, the knapsack 0, 1 knapsack problem. right? Okay, so let's try to code these things up. Oh, and one more thing here, since we're going to do like a target here, right? A target like the uh, we're assuming this target is correct, right? So we have to do some pre-check, sanity check for this like a total, basically the total sum. Basically, if the total sum cannot be divided by two, and then we simply return zero, which means there's no way we can find this target because, right? Basically, there's zero ways we can come with the target here. Mm, okay, cool. So let's try to code these things up here. And yeah, like I said, we're gonna have a total, right? Total is the sums equals the numbers, right? Sum of numbers, and then the okay. Basically, if like I said, if the total plus the target, right, and divided by mod by two, if it's there's still some remainders, we simply return zero, right? Which means there's no way we can come up with that function, right? Else the target, right? Else the target equals to what? Gonna be the like I said, gonna be the total plus s and divided by 2. Okay, and now we can simply define the our 1D knapsack problem array here. So going to be a 0 divided by so not divided, the size is the target plus 1. Okay, and again, so the first one is always 1, right? Which means to get to the 0, to get to s zeros, and we simply just don't do anything. We don't use any of the numbers. Hmm. Yeah. Yeah, basically this DP0 means to get to the zeros, and with the target the zero, and we have zero numbers. There's the base case is 1. There's always one way. Basically, we don't use anything to get to this state, right? That's why we initialize this one DP0 to 1. And other than that, it's just a regular DP uh, knapsack problem here. And so notice here we have already compressed the space complexity from 2D to 1D, and numbers in nums, okay, for and j in range target, right, to num uh, -1 -1. Basically, dpj will be caught. We're gonna accumulate that, right? Mm, dp j minus num. Okay, here we simply return the dp target. So for those who still don't know how can we compress this compress 2D problem, 2D space into 1D space, and you can check my previously I think I briefly talked about that in my change corn like videos. You guys can like take a look at that video to understand how can we how why we're doing this, why how we can improve this thing into 1D, and why we are traversing this inner loop from the biggest number to the smallest number. So long story short, basically, since the current state, for the 2D state, right? Basically, the 2D state is like this: dp I and j. Okay, so so I means for the first for the first i's numbers, items, in this case items, um, to get to j capacity. right? Capacity, how many ways? Okay, so that's the definition of our like original 2D problem, 2D array here. And since the current DP I and J only relies on the DP I minus one, basically I minus one and J, because we can only use the DP use this number once. That's why we have to solely depending on the I minus one state. Okay, and since we are only depending on the previously state, we don't have to remember all the first dimensions here. We can simply remove the first dimension. Basically, this is something like the uh, basically dp I j, right, equals to dp I minus 1j. So this means like the first scenario, for the first current number, we can either choose we don't pick it. That's the state, right? That's the first choice, which means we don't pick the current number. And then the second one would be like, okay, so now we're picking the second number. We're picking the current number, which means if we're picking the second numbers, now the dp I and j will become the previously state, right? But the the capacity will go back to the j minus one, since we have decided to pick this number. That's why to get the current j, the previously capacity has to be a j minus n number. And since, like I said, this I only depends on the I minus one, we can simply remove the first state, right? So that's why we can just simply convert this one to this one. And the reason we are doing this like from the biggest to smallest is because when we calculate the dpj, right? As you can see, the dpj minus j minus num will be smaller than dpj, right? So which means if we doing the loop from the smallest to the biggest, by the time when we calculate the dpj here, the dpj minus n had already been calculated based on the current num, right? Which is not what we want, because we want, when we calculate the dpj here, we want the dpj minus num still is still storing the I minus one state data. That's why if we do the loop from the biggest to smallest, when we doing the dpj here, this dpj minus num has not been calculated for the current num, right? So, but if this is like a complete knapsack problem, then we just need to change this one to a regular smallest to the biggest loop. Yeah. Yeah, other than so that's once it's finished, we just need to return the DP target here. Yeah, I think this should just work. Let's try it. Try it. Oops. Oh yeah, um so other than check this, if the total plus sum can be divided by 2, we also need to check another thing here. As you can see here, so if the S is super big, right? If it's too big that there's no way this numbers can get to the sum, right? The total sum of these numbers cannot get to the total here. The target, which can simply return 0 here. That's basically the ABS of S is greater than total, right? If that's the case, we simply return 0 because there's no way. Oh, sorry. And yeah. Oops, sorry, not and. I think it's or. Yeah. What am I doing here? Cool. Yeah, as you guys can see, Okay, this new DP is super fast. See, because not only it's reduced. Okay, sorry for the time and space complexity. I think, mm, yeah, actually, the time complexity for this one is still the same. That's the number of it's the number of number of num which is n and the s. So s is kind of like the yeah. So the second one is the target is bounded to target, and and the target is depends on the net total and s, right? So which means okay. So I think now I have something I want to talk about here. Mm, see, basically the sum of the elements in the given array will not exceed 1000. And yeah, and I'm assuming this s would also be too big. Yeah, basically, since we are, even though the s is too big, we'll be stopping our algorithm here. We simply return 0. So since the sum of the elements are given will not exceed 1000, so that's which means the s will also be smaller than 1000, right? And then our target will be bounded to basically also to 1000 here, right? So then okay, and then the length of the given array is positive and it will not exceed 20. So in this case, the time complexity for this is going to be the n times the sum, right? The target, the total, basically the total, two times total, yeah, two times total here, and yeah, that's gonna be our time complexity for this knapsack problem, and the space, that's the time of that, and the space is yes, O of the total, right? Since we're doing the 1D. Yeah, and how about this one here? So in this case, mm, yeah, in this case, the time complexity is as you can see, for each of the I here, we have two options here, right? So the number of the subproblem is the 2 to the n, right? That's the time complexity, because for each of the number n here, we have two options, and to loop through all the i's, we'll do a 2 to the power of n. Yeah, and the space complexity is also 2 to the power of n, maybe, because for the memory, so basically the space complexity, yeah, it's gonna be the same. Yeah. Oh, because the DP, we have a recursion here, which is kind of slow, right? Well, actually, so this one may be I mean, since we have these memorizations here, right? So the total time complexity shouldn't be 2 to the time of n. So this time complexity is the time complexity if we just do a brute force recursion without these memorizations. With these memorizations, I think, I mean, it's going to be close to of the n times basically the range of the sum, right? The range of sum, yeah. And the space will be the same, n times the range of sum. because we're not always doing the DP here, because for some time whenever we have to store these numbers and plus the range, this sum will be directly returning from here. So I mean basically I think in that case this time complexity for these two solutions are kind of similar, right? But since we have this like the recursion overhead, I mean where the the compiler or the operating systems have to store some of the state of the recursive functions. That's why the recursive solution is always slower than the iterative solution. Yeah, cool. I think that's pretty much it is I want to talk about for this problem. And yeah, it's a very classic, you can say DP, yeah, classic DP problem. And there are two ways of solving this problem. The first one is the traditional like top-down recursive ways, and this is more intuitive. And but the reason I want to discuss about this problem is I want to show you guys the uh, the the knapsack solution here. Right, this is a very I kind of like it, very elegant and brilliant way of converting this problem into a 0-1 knapsack problem. Mm, cool. I hope you guys enjoy watching the videos, and thank you so much for watching my video, and stay tuned. See you guys soon. Bye bye.